Welcome everyone to the first seminar of spring semester. Today we are very happy to have Zheng Zhou of Perimeter Institute, who will be telling us about how to study 3D conformal field theories on the fuzzy sphere. And we plan to take Zheng to dinner tonight, and we can meet here in the lobby at 6:30 or at the restaurant at 6:45. Okay, and if you're interested in coming, please send Lisa an email by 4 p.m. so we can make a reservation.
First one?
Yes. Was there a question?
Mediterra.
Oh, Mediterra.
What a shocker. What is the original text?
So, good afternoon, everyone. It's an honor to give the first seminar talk this year at IAS. And today I'm going to talk about our recent progress studying the 3D conformal field theories on the fuzzy sphere. So my talk today will be mainly based on these two papers of ours. And I will first give an introduction to critical gauge theories and fuzzy sphere. And then I will focus on two different aspects. The first is the Chern-Simons-Matter theories, and the second is about interacting and free Fermionic CFTs. So as an introduction, coupling critical scalars or critical fermions to a dynamical gauge field is among one of the few known ways to construct interacting conformal field theories in three space-time dimensions. In condensed matter, they also describe various exotic critical phases or critical phase transitions in the infrared. For example, the SU2 QCD with two flavors of fermions, it describes the SO5 deconfined criticality. And the Dirac spin liquid, it is described by the QED with four flavors of Dirac fermions. Despite its importance, few is known about its critical data. As an example, there is a famous conformal window problem. That is to say, under what numbers of flavors does these Lagrangians flow to a conformal fixed point? This is largely unknown in three space-time dimensions. So to make things even more interesting, we can add a Chern-Simons term to the dynamical gauge fields. This gives us the Chern-Simons-Matter theories. These Chern-Simons-Matter theories, they describe transitions between or out of topological orders. Theoretically, they host dualities between different interacting theories. And experimentally, they are also very relevant to, for example, the fractional quantum Hall systems or the Moiré materials. So let us look at a simple example. We take a complex scalar, the phi-4 theory, and couple it to a dynamical U1 gauge field A, and then add a Chern-Simons level 2 to this U1 gauge field. And this describes a transition, that is controlled by the mass term m squared. So when m squared is positive, the bosons are gapped, which leaves us with a pure U1 level 2 Chern-Simons theory. This gives us a symmetry topological order. And depending on different contexts, it can describe the chiral spin liquid or the nu equals half bosonic Laughlin state. On the other hand, when m squared is negative, the condensation of the bosons hits the gauge field A completely, which gives us a trivially gapped phase. So this transition appears in various contexts. For example, in spin system, it can describe a transition between a chiral spin liquid and a paramagnet. Upon doping at this critical point, it can induce the so-called annual superconductivity. And in cold atoms, this transition can be induced by Feshbach resonance. Now, an important feature of these Chern-Simons-Matter theory is the duality. The duality describes that different Lagrangians, they can flow to the same fixed point in the IR. A famous example would be the particle vortex duality, which says that the scalar QED with one flavor of complex scalar, it is dual to a critical complex scalar itself, which is the O2 Wilson fission. This duality has been numerically verified by Dasgupta and Harpuri. On the other hand, more dualities stays at the stage of conjecture. These conjectures are made by matching the global symmetry, matching the phase diagram, which also includes matching the counterterms or the response, and matching the operator content of both sides. For example, the U1 level 1 Chern-Simons coupled to a complex scalar is conjectured to be dual to one free Dirac fermion. For these two dualities, one side of the duality is known. On the other hand, the U1 level 2 with a scalar, it is conjectured to flow to a CFT in the IR with an SO3 symmetry. This theory is conjectured to have three other dual Lagrangian descriptions, namely U1 level -3½ coupled to a Dirac fermion, SU2 level 1 coupled to a scalar, and SU2 level -½ coupled to a fermion. So for these SU2 gauge theories, the SO3 symmetry is manifest as the flavor symmetry. And on the other hand, for the U1 gauge descriptions, the manifest symmetry is U1 topological of the U1 gauge field, and it is conjectured to be enhanced to an SO3 symmetry in the infrared. However, this transition U1 level 2 with a scalar, it is first proposed 30 years ago by Wen and Wu. In the 3 decades, people keep being interested in it. However, what is the nature and its physical property? This is an unsolved question. People cannot use quantum Monte Carlo to study this transition due to the intrinsic sign problem. Conformal bootstrap also does not apply so well to the gauge theories. And on the fuzzy sphere, we have obtained the first answer to this question. So briefly speaking, the fuzzy sphere involves studying interacting electrons moving on a sphere with a magnetic monopole at its center. It has been first applied to the 3D-Ising CFT, where people are able to obtain a wide range of spectrum at very high accuracy, even on very small system size. And people have obtained the first numerical verification of the conformal symmetry of the 3D-Ising transition. So to better explain the idea of fuzzy sphere, we split it into 2 keywords. First, sphere. So we want to study a quantum Hamiltonian that is defined on a d-sphere. This is because combined with the imaginary time direction, the whole spacetime manifold, the cylinder, is conformally equivalent to a flat spacetime through a Weyl transformation, where each time slice on the cylinder is mapped onto a concentric circle. This allows us to make use of some very nice property of the CFTs on the flat spacetime. A very important one is the state operator correspondence, which says that each CFT operator, if it has a 1-to-1 correspondence to an eigenstate of the quantum Hamiltonian that describes the CFT on a sphere. The state and the operator, they have corresponding angular momentum, corresponding quantum numbers. And more importantly, since the Hamiltonian, which sends one time slice to the other, is mapped to the dilatation, which sends one sphere to a larger one, their eigenvalues are corresponding, so that the excited energy of the eigenstate on the sphere is proportional to the scaling dimension of the corresponding CFT local operator. That is to say, to extract the scaling dimensions of the CFT, which is a very important piece of CFT data, we no longer need to do very complicated finite size scalings. We only need to read it off from the energy spectrum. Now, in 1+1D, it is very easy to put things on a sphere. We only need to consider a lattice chain with periodic boundary condition. However, in 2 plus 1D, things get a little trickier. This is because there is no lattice that preserves the full SO3 symmetry due to the curvature of the sphere. So we take an alternative approach. We fuzzify the sphere. That is to say, we use the spherical Landau levels instead of the lattice as the single particle states. This is an idea that first comes from the quantum Hall physics, more specifically coming from Duncan Haldane. Others may call it the Haldane sphere, but Haldane himself calls it a fuzzy sphere. Thus comes the name. The word fuzzy essentially means non-commutativity. And here, the non-commutativity comes from the magnetic field. So we consider electrons moving on a sphere with a magnetic monopole at its center. The magnetic field, it modifies the single particle Hamiltonian and further the single particle eigenstates. Now, the single particle states, they form highly degenerate spherical Landau level. The lowest Landau level, for example, has a degeneracy of 2q plus 1, where q is the charge of the monopole at the center. So if we set the single particle gap to be much larger than the scale of the interaction, and then partially fill the lowest Landau level, we can constrain the quantum fluctuation within the lowest Landau level. So we can project the system onto the lowest Landau level and just throw away everything that is above. This gives us a finite Hamiltonian, which we can study numerically. So we write down the electron creation operator as a linear combination of the creation operators of the orbitals on the lowest Landau level. So now we have these single particle states. To construct an interacting Hamiltonian, the simplest building block is the density operator, which is local fermion bilinears. So for example, to construct the Ising CFT which spontaneously breeds a Z2 symmetry, we only need to consider 2 flavors of fermions on the lowest Landau level, which carries respectively Z2 odd and Z2 even, and add a density attraction that mimics the Ising type interaction, and then add a polarizing field. This transition, by tuning the parameter h, can realize the Ising CFT, and it is in complete analogy with the transverse field Ising model.
And next is the density of spin.
Yes.
The x direction.
Yes. So we have two flavors of fermions,
Okay.
and we insert a sigma x in between.
Can I ask a very stupid
Yes.
question? You don't have magnetic. Why are you, how do you, I don't know.
Yeah, this is just a model to.
But how can you get rid of, I mean, like you said before that we learned something about Ising. Like, but in this context of putting a magnetic monopole inside.
Yeah.
How can you get rid of it so that you still learn something about it?
Yeah. So essentially, the monopole it is just a setup in the UV. It is microscopic setup. It does not enter the CFT in the infrared. That is one explanation. And the other one, this is, if you consider the thermodynamic limit, so we put thermodynamic limit, and we take thermodynamic limit as Q goes to infinity, and correspondingly, the radius of the sphere goes to infinity. This is nothing more than just a flat space-time and acting a magnetic field on it.
Can you remind us what M and U are?
Sorry?
We have an MAB and a U. Can you remind us what they are?
And maybe it's just a matrix that acts on the flavor index. So for example, for the Ising model, we have 2 flavors of fermions. So A, B takes spin up and spin down, for example, and the M can take the Pauli matrices. So it is a matrix.
Which of them?
So for example, for nx, we insert sigma x.
Oh.
And for nz, we insert sigma
What is
z. U is a function of U is a density a potential function of the density interaction.
And what is
Since to reach the Ising CFT, you only need to tune one parameter. So h can be taken rather arbitrarily. For example, what we usually do is we take the U as a linear combination of local and superlocal interactions. We will see some examples. This is just a hand-waving expression that shows you how the model looks like. We'll see some more concrete examples in the following.
Can you say again what determines the number of fermion species you have to use?
And usually you design the model to have the correct symmetry and phase diagram. So for example, for an Ising transition, you need two flavors that in the Z2 even and the Z2 odd representation of the Ising Z2 symmetry. And for example, if you want a SU2 QCD with an SPN symmetry, then you take 2n flavors to form the SPN fundamental rep. So it is based on the CFT that you want to realize. Okay, so this is the simplest example. Using the fuzzy sphere, we have studied many CFTs that people have no idea how to study before. For example, we have studied the SO5 deconfined criticality. We have determined that its nature is pseudo-critical and it has approximate conformal symmetry. We have further extended this model to
what does pseudo-critical mean?
Pseudo-critical essentially means that maybe it's clearer in the context of SU2 So when the number of flavor is large, you have two fixed points that describes the QCD and the QCD gross Navier-Kawa. When you decrease the number of flavor, these two fixed points become closer and closer, and they collide into complex planes. They become complex CFTs. And if the complex CFTs, they are very close to the real axis, then the physics that you observe in this area, we call pseudo-critical area, it is still controlled by these complex CFTs.
An approximate.
Close in what unit? Is 7 close or not?
That's a good question. I think it is compared with the system size of the linear scale of your system. When your system becomes large enough, you will not see this. You will not see this area, but it is only observable when the distance to the real axis is comparable with your system size.
In what units? The distance to the real axis is in units of the dimension of some operator.
Yes, you also need to know the velocity.
But that depends. If you are sitting at this fixed point, there's a relevant operator
Yes.
that takes us to the real line.
Yes.
And this is how you measure distances.
Yes.
We say distance, you mean the units, given by the dimension of this coupling constant.
Yes.
How do you compare that? What do you compare that with? Theory is conformal.
The theory on the real axis is not conformal.
Right. So I'm sitting at the fixed point, it's conformal.
Yes.
And I'm deforming it with some relevant operator, whatever that means. This is to approach the real axis. I want to know when I'm sitting at the real axis, I have a theory which is not conformal. In what sense am I close to the pseudo-critical point?
Since I'm not talking about this today, maybe we can
Sorry.
maybe we can talk about this later.
Thank you.
Okay. So we also use the fuzzy sphere to study new CFTs that people does not know of before. And beyond the bulk theories, we can also study various conformal line defects and conformal boundaries. However, all these constructions, they are based on so-called quantum Hall fermions, or lowest lambda level at integer fields. If we go to lowest lambda level at fractional field, we can actually realize a wealth of topological orders. If we look at the experiment of the fractional quantum Hall effect, each plateau in the conductivity corresponds to a different topological order. So for example, at feeling 1/k, the so-called Laughlin state realizes the topological orders U1 level K. And beyond that is just the simplest example. And there are various billion and non-abelian topological orders beyond that. So if we construct the transitions between them, those are actually the Chern-Simons-Matter theories that we design. So let us look at a first example, the confinement transition of U1 level 2 Chern-Simons. So our setup involves 2 flavors of fermions and 1 flavor of boson. We let the 2 flavors of fermions, they carry the fundamental rep of an SU2 global symmetry. And we let the boson to feel the magnetic field as well. We set its electric charge to be twice of the fermions, so that the lowest lambda level of the bosons, it has twice as many orbitals as the fermions. We allow a conversion between 1 boson and two fermions, such that the electric charge is conserved. So on the one side of the transition, we set the fermions to be completely filled and the bosons to be completely empty. This will give us a feeling 2 fermionic integer quantum Hall state, which is an invertible TQFT. And on the other side, we move all the particles from the fermionic flavor to the bosonic flavor. In this process, the number of orbitals double, but the number of particles become half, so that the boson filling is 1/4 of the fermion filling, which is 1/2. So on the other side, we can realize the nu equals 1/2 bosonic Laughlin state, described by a U1 level 2 Chern-Simons. So for the Hamiltonian, we only include the simplest terms, which are the charge density interaction, which appears as the background interaction in many fuzzy sphere models. And this term also favors the bosonic Laughlin state on the right-hand side of the transition. We include a conversion, a hopping between 1 boson and two fermions. And we also include a relative chemical potential, which we use as the tuning parameter. So when mu is large and negative, fermions are favored. So we can realize the fermionic integer quantum Hall state. When mu is large and positive, we realize the bosonic Laughlin state. So this transition, we confirm it can be described by each of the 4 Lagrangian.
Ask about the chemical potential.
Yes.
So this is what's the U1 symmetry that couples to?
Yes, the U1 symmetry that couples to the chemical.
This is just this is the same U1 that is the charge for the charge that couples to the magnetic field.
The charge that couples to the magnetic field, it is conserved, and in the infrared, the U1 charge is decoupled.
Okay,
So actual conserved charge is NF plus 2NB.
Yeah.
Right?
Yes.
that's right. Is that the chemical potential you're looking?
Yes, it's not this one. The chemical potential, what it does is it adds an extra penalty to the fermions or to the bosons.
Oh, I see. So you're calling it chemical potential, but it's not really coupled to conserve charge. It's just coupled.
No, it is. Yeah.
Okay, fine. Now,
What's it coupled to?
fermion number.
So when
So
mu
the U1 charge of the fermions.
That's not a symmetry.
It's not a simple. But you
Oh,
can
no,
add it
so-
as a term in the Lagrangian. It's just confusing to call it chemical potential. But
yeah, maybe I shouldn't call it. Yeah, so we confirm that this transition can be described by either of the four Lagrangians. So we do this theoretically by matching the phase diagram. That is to say, we can confirm that that either of the four Lagrangians, they have the correct topological order on both sides, and it has the correct response or the counterterms, which include the Chern-Simons term of the probe field, that is the Hall conductance, and the gravitational Chern-Simons, which is the thermal Hall conductance.
Sorry, how do you see all these Chern-Simons terms on the body? On the sphere?
So I think it is given by the conductance. So for example, one flavor of fermion, it has a Hall conductance 1, which translates to an ADA term.
A is dynamical or classical?
Classical. So
But where are the dynamical pH fields that have a Chern-Simons term?
we think they emerge, and what we can say is that on the when the theory is stepped, it has the same phase diagram as the transition that we are studying.
You put this system on your fast sphere.
no, I think my understanding is that these are four theories. He has a fifth theory, which is what he discussed previously.
Yes.
He's arguing that the transition between that fifth theory is the same as the transition between all these theories.
Yes. Thank you.
In these theories, you can tune these Chern-Simons to couplings, B and A, etc. Every one of them is another parameter, integer parameter you can change.
Yes.
What's the counterpart of that in your fifth theory?
I would disagree that you can tune this the Chern-Simons level. So when you change the Chern-Simons level, it becomes a different field. So we need a different construction.
But how do you know that this construction of yours corresponds exactly to these four?
Yeah, that's a good question. So we confirm that on both sides, it has the same topological order. On the one side is a trivial topological order. On the other side, it is a U1 level 2 Chern-Simons theorem. So it has the same.
Do you have to compute Hall conductance and the center charge from wave functions, or how do you? You don't have to calculate.
I think, for example, when mu is infinite, the limit is well known.
So you just write a model wave function,
Yes.
let's say the fixed point wave function, then from that you can just.
Yes.
Okay. You don't have to do any
You
calculation.
can also look at a spectrum.
Yes, that's true. Okay, that's true.
And you get extract, let's say, Hall conductance sum of all these values agrees with the.
Yes.
Okay.
I'm getting more and more confused. What you actually study is this mass, right?
Yes, what I actually study is this one.
What's the role of the other four?
What? Sorry, what?
You gave evidence that the four other theories are dual to each other.
No, this we do not have access to. We actually do not have confirmation that we do not have evidence for their duality. And it is believed that these four theories are dual to each other because they have the same phase diagram. That's the same operator.
There are stronger arguments than that, but I'm still not clear. If I didn't know about these theories, all I had was the Hamiltonian that you wrote on the previous slide. I'll say, okay, I have these two phases,
Yes.
and there's a critical point in between.
Yes.
And then how would I go from these to any of these four Lagrangians? I would learn that there is a fixed point, which
Yes.
has the information that takes me to these two phases.
Yes.
That's all I will know.
Yes. That's more or less what we have evidence for.
So this has nothing to do with the four theories of the next slide.
There are only a few candidates that we know that describes this transition between these two different phases. So it's a natural belief that this transition is described by this theory that we know of that describes this transition. But so far we have no evidence for that.
So
And
if somebody with other theory
yes,
has that, it's either dual to these four
yes,
or might be something else.
yes, it might be something else, but that's the more non-trivial case.
So it could still be that the duality is wrong.
That's true.
And the fixed point that you found corresponds to one of these theories, but not the others.
That's true. But we can go through the critical parameters, and so far, all of this model at all
I'm not disputing your claim. I'm quite convinced that your claim is correct. I just want to see how much of that you can actually substantiate.
What we can say is we have not found another fixed point that describes this transition yet. All we have found is just this one transition. So it's natural to believe that it flows to these four Lagrangians. Okay. Oh, shall I continue? Okay. Yeah. So the first thing we can say is that the transition is continuous. So we perform an exact diagonalization calculation on the fuzzy sphere with our package Fuzzify. And the first thing we have found is that all the observables, they change continuously. And the gap and the energy gap, they closes in the fashion of proportional to 1 over R, which is an evidence for continuous transition. And what is more interesting is about
Sorry, so
yes,
the roll top doesn't close as one over.
yes, we are just confirming that this is
The other
a
one.
gapped degree of freedom that does not interfere with the CFT. And the charge gap also does not close. This means that the U1 charge is decoupled at the critical point. So only the singlet gap or the CFT degree of freedom become gapless at the critical point. Yeah, so the more important information is about the conformal symmetry. So we extract the information of the conformal symmetry through the state of operator correspondence. A unique feature of the CFT spectrum is the conformal multiplets. So we start from a primary operator. By acting partial derivatives on the primary, we get its descendants. And the descendants are at integer spacing with the primary. For example, partial mu s, it has scaling dimension delta plus 1. And partial s has scaling dimension delta plus 2, etc. And we can find that all the lowest lying states, they can be classified into such conformal multiplets. And for the lowest primaries, for example, the lowest singlet and the conserved current, we can find all of its lowest lying descendants sitting nicely at integer spacing.
So in the first picture, that's a singlet
Yes,
conformal family.
yes,
Presumably, I should see this diamond for S equals 1, the second state of S equals L equals 0, etc.
yes. So different symbols are data for different system sizes.
I just mean that it
And-
seems like there's still some pretty large error.
Yes, you can define a cost function to measure how different it is from the I haven't shown this data here, but you can actually find that the cost function scales to 0
Skills.
Yeah.
As you increase,
as you increase the system size.
What you're calling 5, 6, and so on is the degeneracy of each of the fermions. The lowest.
Yes. What we call the system size or the orbital of number of orbitals, yes. And this can for J, you can also have structures that involves the epsilon tensor. And yes,
also, so I remember in the Ising case, or
Yes.
in some other cases that you had mentioned earlier, you have to use, say, one conserved current to fix like the velocity.
yes.
Do you use something like this one?
Yes. So you see, there is a constant factor between delta and E,
Right.
and we determine this constant factor by optimizing the conformal symmetry. That is to say, we use multiple criteria,
Okay.
Both J equals to 2, T equals to 3, and integer spacing.
I see.
We make them the best at the same time.
I see. So not a single one of them,
Not a single one.
but
Yeah.
minimize all of them.
Yes. We are trying to optimize the procedure when we are studying unknown CFTs.
Say again what T was, the third panel. What is the third panel?
The third panel is it carries the SO3 spin 2.
Ah.
That is SO3.
Okay,
Yeah.
scalar operator.
Yes. So it is an anisotropy that breaks SO3 to O2, and we can confirm that this operator is irrelevant, highly irrelevant.
We have to truncate the boson Hilbert space.
No, we don't know that. And since the number of bosons has a maximal value.
Oh,
So for example, when NMF equals 9, there are at most 9 bosons. So it is a finite Hilbert space. Shall I continue? Yes.
Can I ask an ignorant question about a couple slides ago? You said that for this fuzzy sphere Hamiltonian, when you tune this relative chemical potential,
Yes.
you can see that on one side you have this U1 level 2 topological order, and on the other side you have trivial.
Yes.
How do you check that you have U1 level 2 if you only have access to the theory on the sphere?
You can check it by calculating the entanglement spectrum. There is a Laughlin conjecture that the entanglement spectrum has 1-to-1 correspondence with the CFT, chiral CFT on the edge. I can show some results later. Yeah, I have some results later that gives you how do you diagnose these QFTs. Yeah. So we can ask about its operator spectrum. The most important thing is that there is only one relevant operator besides the conserved current. And we have extracted its scaling dimension through a finite size scaling. Its scaling dimension is 1.52. This means and the second singlet is well above 3. This means that it is an genuine criticality, not a pseudo-critical point, not a pseudo-critical region, not a multi-critical point. And this observation is also consistent with duality. So the anisotropy that breaks SO3 to O2 is irrelevant, and things like anion superconductivity, etc. And the fact that delta S is less than 2 means this transition is unstable to against disorder. And we can also look at higher spectrum. Here L is the Lorentz spin, and S is the flavor SO3 spin. And we can actually see that the higher spectrum, it is very sparse. So this makes, with this input, it makes it a very, very suitable target for conformal bootstrap. So each scaling dimension here can be set as a gap for the conformal bootstrap. So as a brief summary of this part, we have studied the transition between a U1 level 2 Chern-Simons theory and the depth phase. This transition can have 4 dual Lagrangian descriptions, and it appears in various contexts. On the fuzzy sphere, we realize it as a transition between a nu equals 2 fermionic integer conformal state and a nu equals half bosonic Laughlin state. We have the numerical evidence for continuous transition and the conformal symmetry. Yes?
Why do you call it confinement transition? What is confined here?
The gauge field is confining. So the confinement transition, essentially, what I mean is it is a transition between U1 level 2 Chern-Simons theory to nothing, to a trivially gap phase. I wanted it to call it a Higgs transition of U1 level 2, but then, as you have said, we're not completely sure that this transition is described by these Lagrangians.
I don't see what's confined here.
The anions are, for example, the anions are, can I say the anions are confined?
No.
You want to say it's like a spontaneous symmetry breaking one form symmetry? Is that?
I'm not completely
There's
sure.
no one form symmetry in this part.
You want level 2?
So it's
But it
coupled to a
matter.
scalar.
Yeah, so
Maybe the word proliferation would.
Yeah, but maybe that would work. It's definitely not confinement. There are no strings in the system, right?
okay. So let's call it the Higgs transition of U1 level 2. Okay, so this is the first study that reports the conformal symmetry and the critical data for the Chern-Simons-Matter theories. What can we do next? The first thing we want to think about is the conformal defects of these gauge theories. So to realize a line defect on the fuzzy sphere through the radial quantization, we only need to put some impurities at the North Pole and South Pole. Now, these gauge theory descriptions give us an ample playground for studying the defects. For example, we can ask what for example, each of these descriptions has a Wilson line, and the Wilson line can be regarded as some kind of defect. And we want to ask, how does these Wilson lines behave? And how do we construct these Wilson lines? A hint for the construction is the defect endpoint operator. So for example, for the SU2 Wilson line, the endpoint of the defect will carry a SU2 fundamentum. So what we need to put is only need to couple the North Pole and South Pole to an external SU2 spin. This behaves just like a boson-Condo defect. So we can also ask.
Can you go back?
Yes.
These Wilson lines, aren't they screened by the dynamic of phis?
I don't think they can be screened. An argument is that the endpoints they carry the projective wrap of the SO3 global symmetry, so they can be screened.
So are the phis. The endpoint is phi, right?
Yes.
So it's phi, and there's a line coming out,
Yes.
and it goes very far.
Yes.
Can I create the 2 pairs of phis
Yes.
in the middle?
Yes.
And just screen the line in breakage?
To say more.
It's a dynamic question.
No, if you make the string long enough, any finite mass of phi, be energetically favorable.
But I think he claims that this defect with the phi in the fundamental of SU2 would carry a projective representation of SO3.
Yes.
So it's
No, but the same is true for the dynamical phi's. There's the same phi, the phi that sits in the.
yes, but the legal local operators of phi are things which are SO3 representations.
Yes.
Right, but I'm just taking a process that I create two phi's out of the vacuum.
Yeah, I'm not disputing your process. I think what he's saying is that there is this defect, but there is a single phi at one location attached to.
That to a line, but he wants to discuss not the phi, but the line that comes out of it.
Wants to discuss a local operator which is at one point and extends in time.
Right, but if it extends in time, I can pair create. You think of it in Euclidean space. It's just the same question. This question is actually identical to the question I asked earlier about confinement. There are no strings in this point, and these lines are not protected by any symmetry. It's the same thing as it Wilson lines in QCD can be screened by quarks.
But you can still ask him.
Yeah, you can still study them, but
It's not protected by a one form symmetry, doesn't mean that it has to be screened.
yeah, it's the same thing. It's exactly the same thing. And in particular, if you try to match them across the two descriptions, I don't see why they should be the same.
Are you saying that because he's, I think, mainly interested in the critical points, are you saying that any line operator in a 3D CFT which can end is trivial or is screened in some sense? That's not.
At the very least, you would need to specify more information, what you mean by the line.
But I think he's arguing that it is non-trivial because it's in a non-trivial representation, projective representation of SO3.
But so are the dynamical fields.
No, the dynamical. All the CFT fields we can observe is in the linear wrap of SO3.
I understand that, but the dynamical fields is the problem of phi. In phi is not gauge invariant, but it is in a projective representation of the SO3. So it can screen the other line. Why would you keep going?
Yeah, I think he's claiming that there's some defect in the CFT whose Hilbert space of endpoint operators transforms projectively under SO3, and that you can interpret as a defect to anomaly, and that implies at least that it's not literally the identity defect, but it could be either conformal or it could be something like a decoupled qubit or something like this. And it's not clear a priori which of those two possibilities it is, but at least it's not a completely trivial defect. I guess you're further going to claim that in fact they're going to be conformal. Is that right?
Yes, we have indeed observed some signature of homosymmetry. Yeah. Thank you. Yeah. The other thing we can ask is about other transitions out of U1 level 2. For example, we can ask about the transition between U1 level 2 to U1 symmetry breaking or SO3 symmetry breaking. These are different, or even SO5 symmetry breaking. These are different Chern-Simons-Matter theories, and this composes a zoo of CFTs. And on the phase sphere, the construction is very simple. We only need to replace 2 flavors of fermions with 4 flavors of fermions. And then the one side is SO5 symmetry breaking, and we can add anisotropy to break it to different symmetry breaking patterns. So we can also study a general framework for QED with or without Chern-Simons. And these are transitions between U1 level M and U1 level N. And we can construct on the sphere the transition between a 1 over N Laughlin state paired with some fermionic integer quantum Hall flavors and the 1 over N Laughlin states. So So examples in this framework are the U1 level 2 Higgs transition and the direct spin liquid. So we can further generalize it to transitions between Jane states, and these are relevant to transitions in the Moiré materials. So despite that, we have answered many questions about this transition. There are some questions that we do not yet answer. These are questions in the QFT level, beyond the deep IR. For example, given a Lagrangian, what is its fate in the infrared? Given two Lagrangians, are they dual to each other? So far, the photosphere can only realize theories in the infrared, and it will be very rewarding to realize the renormalizable Lagrangians. And the photosphere is actually a very good platform to regularize QFTs, because the non-commutativity sets a natural cutoff scale, which cures the UV divergence, and on the photosphere, all the local operators or their correlators, they are non-divergent. So what we want to do, what we want to ask, how to translate the Lagrangians to the photosphere model. So the first step has already been made. The free theories, the free scalar has been realized on the photosphere, and following this, we can ask how to realize free fermion gauge fields or their interactions. So now let us focus on the second step, the fermionic theories, the free fermions. There are actually more reasons to study fermionic CFTs. Some fermionic CFT can have, some fermionic theory can have enhanced supersymmetry. For example, the Gross-Neveu with one Majorana fermion, it has enhanced n=1 supersymmetry, where the fields sigma, pi, and epsilon, they are connected by the n=1 SUSY generator, and their scaling dimensions are locked together. And experimentally, these fermionic CFTs also have cleaner signature. So, but before all these, let us try to realize the simplest instance, the free Majorana fermion. So it is actually difficult to realize a CFT that it contains fermionic local operators on the photosphere. The difficulty is that the microscopic fermions, they experience strong non-commutativity, and they cannot flow to CFT operators in the infrared. So our solution is to use a boson-fermion mixture. So we include one flavor of fermion and one flavor of boson, so that their local combination F-dagger-B and B-dagger-F, they carry no electric charge, so they do not experience strong non-commutativity, and they can flow to CFT operators. This operator carries fermionic statistics, and if we set the fermion and boson, their angular momentum to differ by 1/2, and this operator also have half-integer angular momentum, thus satisfying the spin statistics. So our model again contains an electric density interaction, a conversion between two bosons and two fermions, and a term that favors fermion or favors boson. We set the total filling to be 1. So when everything is fermionic, it realizes a fermionic integer quantum Hall states. And when everything is bosonic, when the boson filling is 1, it realizes the so-called bosonic Laughlin state, which is described by a SU2 level 2 Chern-Simons theorem. And numerically, we have observed an intermediate phase. So the transition between the intermediate phase with the fermionic integer quantum Hall or U1 level 1 and the intermediate phase with the SU2 level 2, they are both continuous. So the energy gap both closes.
What's the phase in the middle? I can't read.
TSC.
It is supposed to be unreadable so that I can introduce in the next slide. Yes.
It's an invertible phase.
Yes. So how do we determine the nature of the intermediate phase? We determine it through calculating the entanglement spectrum. So there is a Li-Hao-Dan conjecture that says that the ground state entanglement spectrum of the TQFT has a correspondence with the spectral counting of the chiral CFT on the edge. And from the spectral counting, we can actually determine that the chiral mode is three Majorana fermions. Thus, it is described by a SO3 level 1 Chern-Simons theory. It is an invertible TQFT with a chiral center charge 3/2.
If we study like the system on a half sphere, hemisphere,
Yes.
would you see the same edge states?
So supposedly, but we haven't tried that. What we mainly do with the hemisphere is we study the boundary CFTs.
This is
But yeah,
presumably easier than that. In the gap phase.
I think the common belief is that calculating the entanglement spectrum is easier than calculating the spectrum of hemisphere. Okay.
Can I ask a question?
Yes.
Do you at some point make some kind of choice about like boundary conditions of the entanglement cut when you're computing the left-hand side?
I think people do not yet know how to do that.
Okay. Because in principle, the TQFT could have many different chiral edges,
Yes.
but you're finding one of them. So I wonder if at some point you made some implicit choice or something.
Yes, I think the common belief is we do not yet know how to take the different boundary conditions.
Do you have something like orbital cut to a
Yes, we
space cut? You do orbital cut.
We can do both.
You can do both. Okay.
Yes. And this figure, I think, is from the real space cut.
Sphere space.
Yes, but the orbital space cut gives you exactly the same result.
Exactly same.
Exactly the same
Counting, yeah.
counting.
What is the orbital space cut?
So there are orbitals that are loosely speaking localized in real space. So each
I
orbit.
see you say m bigger than 0 versus
Yes,
n.
yes,
Okay,
yes.
fine.
Yes. And now we can look at the transitions. So the first transition is between two invertible TQFTs, which has the gravitational Chern-Simons term 1 and 3/2. So naturally, we can expect that this is described by a single free Majorana fermi. And indeed, we can see that the spectrum has exactly the correspondence with the spectrum of Majorana fermion, and all the scaling dimensions scale towards scales towards integers in the thermodynamic units. Yeah. And
So just to answer, these are invertible theories, right? So the U1 level 1 is an invertible theory it's a classical theory, not quantum.
it's invertible in a sense that it does not contain any endings. I'm just trying to say it's
The
a
degeneracy on this of the torus, there's only one state.
yes.
This is not the same notation you used earlier.
The same notation of
Label theories.
yes. I think this might be easier for a high energy audience. Yes, and the local fermions again can be realized as the boson-fermion bilinear. So the Majorana fermion it is a two-component spinor, and the two components are realized as B dagger F and F dagger B. And we can indeed see that the correlation function it scales towards the conformal correlator. And what is interesting is that if you take that chi equals these two component stuff, the Hamiltonian on the fuzzy sphere can be rewritten in a fashion that is exactly corresponding to the QFT Hamiltonian of a single Majorana fermion. This hints at us that there might be some correspondence between fuzzy sphere and the Lagrangian QFTs. Now we can put different theories on the fuzzy sphere together. For example, the free Majorana and the critical real scalar or Ising. They have something in common. They both involve a so-called reference flavor, the fermionic flavor in Majorana and the Z2 even flavor in Ising. And the CFT ground state has substantial overlap with this reference state fully filled. And there is another excitation flavor, the boson or the Z2 alt flavor. So the hopping between them realizes the elementary fields chi or sigma, and the density of the excitation is corresponding to the mass fields pi bar chi or epsilon. So we can stack these two setups together. We come up with three flavors, one bosonic and two fermionic. And we set the hoppings to correspond to sigma and chi respectively, and the density to be chi bar chi and epsilon. Yes?
When you say bosonic, it's for this sphere is also a two-flavor fermion. Additional two-flavor fermion to realize this bosonic layer. Is that right?
We put literal bosons on the lowest level.
Oh, I see.
Yeah.
Okay.
We put bosons on the lowest level.
This is unlike the Ising CFT, where it's really fermions.
No. So if it is a bosonic field, we need two fermions. If it is a fermionic field, we need one boson and one fermion. Yeah. So in a similar fashion, we can translate the super-Ising Lagrangian term by term to terms on the fuzzy sphere. For example, the Utah coupling involves sigma chi by chi, and sigma here is just the hopping between 0 and 1 flavor, and the chi by chi is just the bosonic density. In this way, we have realized the super-Ising theory, and we can see that the operator spectrum has exact correspondence with the super-Ising theory, and we can for the lowest lying states, we can find that they form the super-conformal multiplets with half-integer spacings.
Is the supersymmetry something that exists in the continuum limit, or is there a remnant in your theory?
No, the supersymmetry is not manifest. It is emergent. Yeah. So my talk today is I would like to acknowledge my collaborators, Davide Gaiotto, Yingchen He, and Chong Wang at Parameter. And my talk today is mainly based on these two papers with them. And as a final summary, we have studied the first Chern-Simons-Matter theory on the fuzzy sphere, the U1 level 2 with the scalar. We have found this transition continuous and conformal and studied its spectrum. In the future, we want to study the defects of the gauge theories, the other various Chern-Simons-Matter theories, and we have also studied the first Fermionic CFTs, the free Majorana fermion, and the super-Ising theory on a setup with boson-fermion mixture, and we realized the local fermions as boson-fermion bilinears. And we have established a correspondence between the fuzzy sphere model and the Lagrangian. And for the super-Ising theory, we have observed an emergent super-conformal symmetry and agreement with bootstrap. In the future, we want to study more about how to regularize Lagrangian QFTs on the fuzzy sphere, and we want to make connection with previous attempts, for example, the non-commutative field theories. And we want to also explore the ideas of this fuzzy supersphere, which gives us an implementation of manifest supersymmetry. And the key message here is that we connect fuzzy sphere with the fractional quantum Hall effect. Using the fractional quantum Hall effect, we can study many theories on the fuzzy sphere that we do not know how to study before. On the other hand, fuzzy sphere gives us a tool to answer many questions about fractional quantum Hall transitions. And last, we noticed that all of the setups today all involve the mixture between bosons and fermions. So it is really a boson-fermion paradigm. Thank you for listening. Yes.
When you regularize a theorem in lattice, you know that you expect to get the CFT and then plus some other irrelevant operators that have to do
Yes.
how you break the lattice symmetry.
Yes.
How,
Yes.
how the lattice breaks the continuum symmetries.
Yes. Yes.
Is there here some story about what irrelevant operators might be present due to the fuzzy sphere?
And the irrelevant operators, they must be singlet under global symmetry, singlet under under Lorentz symmetry.
Yes. But I mean, you're breaking some of the Lorentz symmetry, so.
And the Lorentz symmetry, I think, is fully manifest on the fuzzy sphere.
Well, only the rotation symmetry.
Yeah.
The symmetry between time and space is not manifest.
So on the fuzzy sphere, we have the SO3 rotation symmetry.
Right, that's manifest.
Yes, and we are studying 3D CFTs, so the Lorentz symmetry there in the Euclidean signature is also SO3. So
That's the rotation around the one point in the Euclidean space.
yeah.
But then I can translate and try to rotate around some other point, then that would not be manifest.
That's true. So out of the conformal group, what is manifest is the dilatation and the rotation.
Right. Exactly.
And here, the translation and the special conformal transformation is not manifest. Yeah.
So one question is, what's the lowest dimension operator that preserves the symmetries that you do here and violates the other symmetries? That will tell you how fast you approach the critical value.
Yeah, I think that's that you can only answer case by case. So let us look at some examples. So for example, for the Majorana fermion, you actually only have one relevant operator. And I think the next operator is a descendant of this Kabbakai. So
what's the lowest dimension operator that preserves the symmetry of your problem but violates the full conformal symmetry? That would be the deformation.
I think it will be the box Kabbakai operator. For example, for the Majorana, it's all the operators with finite Lorentz spin are forbidden. So you can look at only the spin zero sector.
Spin, you mean spin under the SO3?
That's true.
Okay.
Right, that makes sense.
Yeah, and the lowest operator is Kabbakai. This is our tuning parameter. And the higher operator is the leading irrelevant operator you are looking for.
In this case, is that a descendant?
Yeah, it's a descendant. Yes, I think there's no more primary in this sector.
So I guess if you want to do conformal perturbation theory, you would need to add scalar primary, leading relevant scalar primary.
That's true, which seems that doesn't exist in this case. That's why this model works so well, even for
It doesn't exist. Does it exist within your
So this
computation, or the system clearly has these operators?
For example, if you take the free Majorana fermion, the only scalar Lorentz scalar primary you have is the Kabbakai. And you do not have a higher Lorentz primary, I think.
For example, in the Ising case, you would have some.
Yes. Let us look at another case. Yeah.
Why don't you have others?
You have the one he said, and then you have currents. with two
So there's an
fermions.
infinite number of operators with spin zero.
The descendants.
All of them are descendants.
Are you talking about two fermion operators or are you talking
They're
about
operators
four
with four
fermions or 10
fermions.
fermions?
Eight fermions.
Maybe it is very high. I take it back. It should be very high.
So they exist, but they have very high dimension.
Yes, yes,
So maybe it works so well because the leading operator has such high dimension.
yes. So for example, for the SU2 level 1 Higgs transition, what we have is so the same dimension we observe is a function of the system size. And here different lines we tune another parameter, which is equivalent to tuning an irrelevant operator. We see that these lines go to the same value at a power, and this power essentially determines the scaling dimension of the irrelevant operator, which is this operator. So indeed, we see that the finite size
The
effect
one you
is,
pointed to is the one that has dimension 3.7.
yes. Yes,
Can I ask a question about line defects?
Yes.
So in one of your motivational slides, you said that the main reason to consider fuzzy spheres is because it's hard to, maybe impossible to manifest SO3 on the lattice. Now, when you insert a line defect, I guess you're only preserving the U1 that rotates around the north and south poles. So is there still a compelling reason to treat this with fuzzy sphere as opposed to a lattice regularization, or?
here you still have the state operator correspondence. So you can read the defect spectrum from the energy spectrum in this setup, and you cannot do that for guys.
Why can't you do it? It seems like it's analogous to the situation in 2D where on the lattice you can't manifest the full U1, but you can manifest a,
Here it preserves all the symmetrical defects. As much as
well, there's
there
the
can be,
transverse U1.
and then the conformal, not all of it, but the conformal symmetry is not.
Oh, but I thought, do you preserve anything besides the transverse U1 and the dilatations?
Out of the defect conformal group, we preserve only the U1 rotation and the dilatation. Indeed. So of the defect on the fuzzy sphere, we can still interpret it as the radial quantization of a defect configuration, so that we can still make use of the stereo operator correspondence. And you cannot do this for example, defect on lattice. You cannot interpret it as the radial. You cannot make use of such nice properties of CFTs.
Why not? Maybe that's the part I didn't. If I put a lattice on the sphere that preserves the U1 rotation.
Oh, this I think.
Or is that, sorry, not the U1, but a discrete subgroup thereof.
This
I calculate the energies on the sphere with the defects inserted.
This I think you can indeed do. Yeah, you can do that, but I don't know whether anyone has tried that before. Yes.
Can I ask about your examples of the emergent supersymmetry? Normally, it's hard to think about supersymmetry emerging at low energies if it's not present microscopically, because there's all kinds of relevant operators that only supersymmetry actually has. That's why it's so hard to put supersymmetry on the lattice. There are sort of dumb examples, like you can have you can arrange to get a massless Majorana genome together with the gauge field accidentally becomes supersymmetric. But anything with scalars, you're doomed. Right? So how's it working in your examples? How are you managing to get an emergent supersymmetry? I didn't see the details of the details went by quickly. Do you have massless scalars in these examples?
So here, like you have said, we have many relevant operators. So we actually have to tune three
Oh,
parameters.
Fine, all right.
Yeah, it's just fine tuning is easier on the fuzzy sphere than on the lattice. So what we have to tune, we have to tune away the sigma, the epsilon, and the sigma prime. We have three tuning parameters.
Because you're maintaining more symmetries.
That's true.
Okay, fine, sure.
I have a related question. The symmetry that is built in is the rotation symmetry of the sphere.
That's
And
true.
this one interacts in a quite complicated way with supersymmetry.
Yes.
So I don't even see the symmetry group that you're going to tune to it.
So
It's slightly different. It's in the same neighborhood as Rima's question.
Yeah.
Well, I think he doesn't care though, because just a total number of relevant operators is smaller for him, I think. And than it would be for a garden variety.
How much, right? I think the way it's traditionally been thought of, you got translation symmetry. Now you want to tune also the supersymmetry.
Right.
He doesn't have translation. He has translation on the sphere, let alone that it's also not commuting. That's not part of the supersymmetry algebra. It's very hard to get supersymmetry on the sphere. So that's why I'm questioning which symmetry is it that you have and which symmetry do you tune?
So what I have is only the SO3 sphere rotation symmetry.
Right.
So anything that is not in this column is forbidden. Any primary, conformal primary in this column is allowed. So I don't have parity either. So what is allowed is this sigma, this epsilon, and this epsilon, this sigma prime. That's three tuning parameters. And we indeed tune three parameters on the fuzzy sphere to reach this rate.
As opposed to how many, if you're just doing something dumb? I mean, just what's the total number of relevant operators if you're just a naive continuum person? How many more, just to have an idea? I mean, there's some scalar mass, there's some.
It's meaningful only if you say which symmetries you impose. And the symmetries he imposes.
Well, I'm comparing to what you do on the lattice, on a conventional lattice. I just want to have an idea.
On the lattice, you relatively easily get the translation symmetry. He doesn't have the translation symmetry, he has the rotation symmetry. The rotation symmetry interacts in a very complicated way with supersymmetry. So in order to get current invariance,
Yes.
so that's a subgroup. And I have the subgroup, and I'm only interested in those operators that preserve the subgroup. But for supersymmetry, it's different. So it might be that you're lucky, and once you got the Lorentz invariance by tuning the appropriate numbers, then you get also the supersymmetry.
Yes.
But that's far from obvious. But the point is that the SO3 that you have
Yes.
is not a subgroup of what you're trying to get.
It is not.
If you just imagine you have a continuous sphere.
Yes.
So imagine you do the limit and you have a continuous sphere with exact SO3.
Yes.
It's not easy to put supersymmetry on the sphere.
I'm not implementing supersymmetry on the microscopic level. I let the supersymmetry emerge. So
Also have the super-conformal symmetries. Oh. Maybe
the rotation is a subgroup of the super-conformal group.
Can we go back to your just simplest example under Lagrangian, just the simplest supersymmetric model?
Yeah.
This one, right? So like super naively, if you're going to try to get this theory to merge on the lattice, you've got to tune, of course, you've got to tune the scalar mass is 0, and you have to tune for the relation between the, are there relations between couplings here or no?
Yes, you have to have a relation between.
Exactly. Yeah. So you have to tune the relation between couplings. Anyway, I don't know how many, but there's maybe 4 or 5 things you have to tune to 0. Is the difference, are you saying that on the fuzzy sphere, you only have to, which one of these happen automatically on the fuzzy sphere versus on the lattice? That's, I think, my question. I mean, if we compare doing it on the lattice, it's like, I don't know. I can't count, but maybe it's 4 or 5 tunings. You're saying there's 3 tunings. The tunings are ascend masses to 0 or equal and equate couplings that are related by supersymmetry. Right?
I think you have to have a relation between this lambda and g.
Yes, exactly.
And I think this is this happens automatically. This is not relevant.
Okay, good. So somehow that relation between the couplings emerges automatically from the fuzzy sphere, from the underlying model? Why?
So you have mass of sigma and mass of chi, you have both of them you have to tune.
Yes.
And then the relation between
So what I have to tune is mass of sigma, mass of chi, and a polarizing field, which is also allowed. These three are my tuning parameters. This above, I let it happen naturally.
So lambda and G, which are related in the supersymmetric field, that's done automatically.
I think that's done automatically.
Wow. How? Can you explain how? Can you explain why it happens that those things are related?
I think it's because they are irrelevant operators.
Yeah, they are irrelevant. So the scaling that the operator
Oh,
that
these are
comes.
all irrelevant.
Yeah, these are irrelevant.
Oh, okay, fine. Yeah, thanks. Sorry, I'm sorry. We're in.
I think you can tell this from, for example, conformal bootstrap results.
So in free field theory, they're not.
That's true.
In the symmetry that you this starting point assumes that you have Poincare symmetry.
Yes.
And then you say you achieve Poincare symmetry. Now you ask how many different parameters do I need to tune to get supersymmetry?
That's true.
But you don't have, you have to tune something in order to get the Poincare symmetry.
You mean the super-conjectured?
You can better. Yeah.
So what I'm saying is that you have to tune all these terms on the second line to be 0, and you have to relate lambda to G. This is all that you need to do. You agree on that?
In the connection. If you assume Poincare symmetry.
Yes.
is also emergent.
Right, but it's emergent because you tune something. You have to make sure that the way to organize it, there are some symmetries that exist in the problem. It's rotation symmetry.
Yes.
And you look at the target and you ask, whatever I can use the symmetry that I already have, how many additional ones do I need to tune in order to get super Poincare?
Yes.
And how many of them are relevant?
What is the operator that violates the Poincare symmetry? There's no.
Let me say differently. If you put the continued theory, which is supersymmetric, and you tune all the parameters at supersymmetric in the continued is Lagrangian. We put it on the sphere.
Yes.
Is the spectrum supersymmetric? The answer is no. The exact continuum theory, which is supersymmetric, you put it on the sphere, it's not supersymmetric.
Okay.
Because the sphere does not preserve the supersymmetry algebra.
That's true. So you need the super Poincare part to emerge.
Sorry, I thought you could put it on the sphere in a way that does preserve some modified version of the super.
That's, you need to work in order to do that. But if you just take this Lagrangian, it is, and take this Lagrangian and tune the parameters to be supersymmetric, put it on the sphere,
Sure.
it will get only through the metric, through the same first term. And if you just put it on G, the result does not preserve any supercharge.
But this modified SUSY algebra, that does contain the SO3 as a subgroup, right?
There is a way to put supersymmetry on this figure, but it's not with this Lagrangian. It's this Lagrangian plus some correction terms.
Sure, I just mean
The
going,
correction terms need to be tuned so that the model is supersymmetric.
right. I think you, but originally you were asking about his fuzzy sphere model. Is it correct to just say that he's tuning until the SO3 that he has in the problem becomes enhanced to the modified SUSY algebra on the sphere?
No, the way I understood what he did, he had SO3 on the sphere.
Yeah.
And he tuned the parameters such that you get the full Poincare symmetry.
But he's on the sphere, so there's no Poincare, right?
Whatever you have the full SO form, whatever it should be. Full.
And also
Get
supersymmetry.
supersymmetry for the ball. I thought supersymmetry should come for free. That's a surprise here. Take this model, you need to be conformal, and you get for free that it is super conformal. This is fascinating. And the question is, why did it happen? Normally, if you take it, this is not true. And it's particularly puzzling because when you put in standard Poincare invariant theory like this one, you need to be supersymmetric. You put it on the sphere, you do not preserve supersymmetry.
So in the same model, you could also tune to other points where you
That's-
realize icing.
That's true.
Majorana.
That's true.
Right? You tune 3 parameters so you get to this super-Ising with some additional fine-tuning, not just tune it so that it has conformal symmetry.
Right, but what is it that you could be tuned to get it?
3 parameters, I guess.
I guess it's conceivable that, I mean, certainly it happens in examples I know in 4 dimensions that when you just ask for the beta functions to vanish, it just happens to force the relation between the couplings that makes it accidentally supersymmetric. That definitely happens. Maybe it's like that.
The question is this a property of this field theory, regardless of how you
Or putting it on the fuzzy sphere in general.
Right.
Well, in examples, yes, right.
Is it because the fuzzy sphere has something smart in it? It doesn't.
I think Mong was saying that you needed additional parameters, right? How many fixed points does this theory have? Is there a line of fixed points?
So if you're asking about the fixed points,
Yeah.
it can flow to Ising, free Majorana, and super-Ising.
But there's no exactly marginal, it's just some discrete fixed points. Is that what you're saying?
There's no exactly marginal.
There's no exactly marginal operator. So
But I guess he's then tuning some
that makes it
relevant operator, and at some point,
Yeah.
So there's some 3-dimensional Fermion space, and
Yes.
there's codimension probably. There's some large codimension Ising and Majorana
Yeah.
submanifold, and there's a one isolated part of super-Ising. You just need to get to that.
Yes.
Yeah.
Yes.
Yeah, I guess the point is, since if they're isolated, one of them is supersymmetric, so you're going to get there. Some basis of structure. But the supersymmetry is kind of accidental. I mean,
Yes, it is accidental. And our knowledge about the spectrum of super-Ising tells us that there are only 3 relevant operators. For example, what you see, sigma to the power 4th, it is slightly irrelevant. It is string dimension 3.7 or something like that. So it is irrelevant. You do not need to tune that.
Thank you.
well, let's thank Frank again.